All right, so for the second talk of this BruCON edition, Mathy is here again. People that visit BruCON earlier or followed the talks know that Mathy has been with us previously, and his thing is everything related to Wi-Fi. So this time he's going to talk about how you could use commodity hardware to actually do advanced Wi-Fi attacks. So please give me a round of applause.
Okay, hello everyone. First and for all, thank you for coming to my talk, and thank you for the introduction. So I am Mathy Vanhoef. I'm a PhD student at KU Leuven, and my main interest is in wireless security and basically all the things around it. And today I will present the talk Advanced Wi-Fi Attacks Using Commodity Hardware. And basically what we will do is we will present a few low-layer attacks on the physical layer against Wi-Fi using very cheap devices. And we won't stop there. We will also show how these attacks actually enable attacks against higher-level protocols. And there will also be demos during the talk, so fingers crossed that they will work here. They are Wi-Fi demos, and there are a lot of people around, so there is a chance that they might go wrong, but hopefully everything will be okay. So to start with the talk, first I'm going to give a very quick introduction about the Wi-Fi protocol. And as most of you may already know, Wi-Fi basically assumes that each device behaves in a fair manner. And what do I mean with that? What I mean with that is that if a device wants to transmit a packet, the first thing it does is it checks, is someone else already transmitting? And if that's the case, it will wait with transmitting the frame itself. And even beyond that, it will actually wait a few microseconds after that transmission is done to give the other stations a chance to transmit as well. And if every device sticks to this protocol, we actually get a fair division of the global bandwidth. Now, of course, it is well known that if you have some expensive hardware, for example, the USRP shown here, that we can basically implement this Wi-Fi protocol ourselves, and we can do whatever we want. So with this hardware, we can transmit whenever we want, we don't have to stick to these rules, and we can behave selfishly. You can do even more nefarious things. If you have a USRP or any kind of other software-defined radio, you can even implement a continuous jammer, which basically constantly emits noise and makes the channel completely unusable. And one of the more advanced attacks, which is actually quite difficult to implement, is a so-called selective jammer. And what does a selective jammer do? It doesn't just jam the complete channel, it is actually able to specifically block certain packets only. So the way this selective jammer works, it is actually able to decode the header of a packet, and based on information in this header, for example the source and destination address, it can decide to jam the remaining content of this packet. And this is an attack that is quite difficult to implement because your device needs to process the frame fast enough, it needs to decode the header fast enough, and then needs to be, again, fast enough to jam the remaining content of this packet. So while people know that these attacks are possible, generally it's assumed that you need expensive equipment in order to pull this off. In particular, the selective jamming attack is widely believed to be only possible using these USRPs. So what will we show today? Today we will show that you don't actually need these expensive devices. You can use a very cheap Wi-Fi dongle, for example, like the one I have here. We can reprogram the firmware of these devices, and we can actually perform these attacks ourselves. And these devices are quite cheap. Last time I checked, one of the cheapest versions was only $5 on Amazon. Maybe by this time they're cheaper, or maybe they'll become more expensive after this talk, who knows. But what we're going to do today is basically I'm going to explain how we can implement this selfish behavior on these cheap devices, and then we're going to test this in practice to see what the most optimal strategy of an attacker is, so we know as a defender how an attacker will behave. And we're going to continue with that, and we're also going to build a continuous and even a selective jammer. And we're not going to stop there. Once we have these low-layer attacks basically against the physical layer, we're also going to show that these attacks allow reliable manipulation of encrypted traffic. So I want to stress here that we are talking about just manipulation, for example, to reliably drop frames or modify packets, and that is useful to actually launch real cryptographic attacks. Because if you want to attack a cryptographic protocol, generally you want to be able to drop very specific packets reliably or make reliable modifications. And the main takeaway point of this talk is basically that we no longer need very expensive equipment to implement these things. A cheap device is enough. In other words, these attacks are cheaper than expected, so as a defender you should at least be able to detect them. Let's say, for example, you have a security camera which works over the same frequency as Wi-Fi, then you should at least be able to detect that you lost connection to this device. It may be because the battery ran out of the camera or something else, or it might be because there is actually an attack going on. All right, so let's get started. The first thing that we will do is we're going to implement this selfish behavior. I'm going to show how to implement it using our devices, and then we're going to find out the most optimal strategy which an attacker can use. Now, to explain this, I'm first going to give a quick background of what happens when a Wi-Fi station wants to transmit a packet. So let's say that we are a device, we want to transmit a packet. The first thing that we're going to do is we're going to check, is someone else already transmitting? And let's say in this case that the channel is in use. We wait until the transmission is done. And after that, we also wait a very short amount of time called the SIFS interval. And the reason devices wait this time period is to allow the receiver to process the incoming frame. Basically, the receiver needs enough time to copy this frame to memory and to put its antenna back in receive mode, so it is ready to receive the next frame. After that time interval, we wait another time interval called the AIFSN interval. And the length of this interval depends on the priority of the frame. For example, if you have voice data, which has a high priority, this time interval is actually quite short. While on the other hand, if you have background internet traffic, for example, you're just visiting a website, this interval is a bit larger, giving this a lower priority. And the final step, well, almost the final step, is to wait a random amount of time, and that is to avoid collisions with stations that are trying to transmit at the same time. And if during this period there is no other station which is transmitting any traffic, only then can we send a device. Of course, these are the steps taken when your device behaves normally, when it behaves according to the Wi-Fi protocol. Using our cheap Wi-Fi adapters, we can actually change this behavior. And just as a note, we are changing the firmware, and this firmware is actually open source. So what can we do? Well, first and for all, we have this random backup period. We can disable that. I will explain how we can actually disable that in a minute. Then we also have these other intervals, and it turns out we can also reduce the timeout of those intervals and essentially set them to 0. So basically, an attacker can immediately transmit after the channel is no longer in use. But what's the optimal strategy of an attacker to really increase its throughput as much as possible? Well, after doing some experiments, we found out that the best thing an attacker can do is to disable backoff and set this time period, which is used to define a priority for the packet, to 0. And in one specific instance, this actually increased the bandwidth from 14 megabits to 37, which is quite a significant increase. And it turns out that if we reduce this SIFS timeout, then we're actually going to decrease our throughput. You may think that's surprising, but actually it's not, because this SIFS timeout was put in place there to allow the receiver to process, to prepare itself to receive the next frame. And if we start to transmit frames too fast after one another, the receiver simply doesn't have the time to process the incoming frame, and it will lose some packets. There is one really important remark that is in place here though, and that is that we can, in general, we can only change the behavior of the client. We can't change the behavior of the access point because that is not under our control. So what does this mean? That means we can only influence the upload bandwidth. Because when we are downloading something, in general, it's the access point that is sending data to us. We cannot influence the access point, so we can't increase the download speed. However, when we are transmitting something, we are uploading something, and then we can play around with all these parameters. Okay, so that covers the things we can disable, but how do we actually disable that in practice? Like I mentioned, we have open source firmware, and this firmware is able to control the actual radio chip through memory mapped registers. And in my opinion, controlling the radio chip turned out to be actually surprisingly simple, because let's say, for example, we want to disable the backoff period as shown here. Well, we simply take the register that holds the configuration for this backoff behavior, and we set the correct bit in this register, and you're done. Backoff has been disabled. Similarly, for these other timeout intervals, there's also a register responsible for configuring these intervals. You again can write the correct value to this register, and you are done configuring the radio. So in my opinion, this was a bit simpler than expected. The only difficult part is really finding out where these registers are located. And the second thing you also have to be careful about is to realize where this code is being executed. Now, I already mentioned that we modify the firmware, but in principle, if you have a normal computer, you have this common layout, and you might expect that this could also be implemented in the driver. However, this is not the case. The modifications that we make have to be done in the firmware. Why is that the case? Well, if you look at our Wi-Fi dongle, it actually consists of two chips. We have one CPU that is basically responsible to communicate with USB, with our main host. And it is only this CPU that can directly talk to the radio chip, at least for our devices. And this, of course, means that we need to run code on this CPU, thus we have to control the actual firmware. Okay, so we know that this selfish behavior is possible, but what can we do to defend against it? Well, there's actually a research prototype called DOMINO, which is able to reliably detect this kind of selfish behavior. So if you notice this, that this is taking place, you can look up this system and try it yourself. For the types of attacks that I just discussed, this works quite well. However, there are some flaws in it, and we will come back to this later. So what I talked about now is if there is only one single selfish station and all the others are behaving normally. But what would happen if there are two selfish attackers which basically want to transmit both at the same time? In that case, what I've at least commonly been told is, well, if there are two simultaneous transmissions, there's a collision and both frames will be lost. It turns out that this is actually not the case. What happens is, if there is a collision, generally the device which has the best signal quality and is using the lowest bitrate, the frames, the packets of that device will get decoded correctly. And that is called the capture effect. I'm going to show a very quick demonstration of this capture effect based on FM radio. So I'm going to show a quick video where a guy is using a handheld radio device and is listening on a certain frequency. And on this frequency there are two radio channels transmitting at the same time. So in principle there is a collision going on, but you will notice that generally one of these radio stations will win the collision, and that's the radio station you will hear. So let's try starting this demo. So here, this guy will be walking around, and because he is walking around, and due to the objects near him, the signal quality of certain radio channels that are transmitting will change. So at different points along the walk he's taking, different radio channels will win. So you can clearly hear radio channel 1 is winning. But as he walks around, you can notice that at times a different radio channel is actually winning this collision. So this is just a quick illustration that there are actually two transmissions on the same frequency. However, one of them is generally winning the collision. And the same is actually true for Wi-Fi. If we have two transmissions at the same time, generally one of those will get decoded correctly. And as an attacker, you can abuse this. For example, so let's say we are an attacker and there are now two selfish attackers which are trying to transmit at the same time. As an attacker, you want to win of the other device. And how can you do this? Well, you can improve your signal quality, so you can increase your transmission power, or you can lower your bit rate. So if there are more than one selfish stations, they will try to beat each other by lowering the bit rate, and they will do this until there is no more advantage. So basically they're playing a cat and mouse game. You have your first device which lowers the bitrate and will then win this collision. In response, the other device will lower its bitrate even more, and so on. And basically this is a bit surprising because you have selfish stations which really want to increase their throughput, and to do that they're going to lower the bitrate, which is a bit counterintuitive. However, if you think of this in a different light, basically this selfish attacker number one will see all the other attackers as background noise. And what do you do if there's background noise? You lower the bitrate. So it actually does make sense that if there are more than one selfish devices, that they will lower their bitrate in order to beat the others. So now for the, in my opinion, more fun part. We're going to build a continuous jammer, and we're also going to, after this, build a selective jammer. So what do we have to do if we want to build a continuous jammer using our very cheap devices? Well, the first thing we have to be able to do is to instantly transmit a frame, whether or not there is already a transmission going on. And to do that, we simply have to disable carrier sense, and carrier sense is the mechanism which devices use to detect if someone else is already transmitting. And finally, we want to ensure that we are constantly transmitting data without any interruption whatsoever. And in principle, we can do this by queuing an infinite amount of packets. However, devices don't have an infinite amount of memory, and these Wi-Fi dongles that we are using have even less memory. They almost have nothing. So how can we assure that there is always a packet that is ready to be transmitted? Well, to answer that question, we basically have to look at how a device is queuing frames that it has to transmit. And basically, we have the radio chip responsible for actually sending frames, and it has a linked list of frames that it has to transmit. So basically, it has a queue of frames that have to be transmitted. And how do we now assure that basically an infinite amount of frames are being transmitted? Well, it's actually quite trivial. We simply change this to a circular list, and we are now sending an infinite amount of packets without any interruption at all. So I did a few experiments using this to test how effective it was. And in principle, this jammer is actually sending valid Wi-Fi packets. However, only the very first Wi-Fi packet that we inject will be properly decoded by other Wi-Fi devices. So what this means is that if my continuous jammer is running, even though in principle it is sending valid Wi-Fi frames, if you put your device in monitor mode, you won't see any traffic at all. There will be nothing. So you have no idea what's going on. The second interesting remark is that this jammer jammer doesn't just basically corrupt other frames, it actually is silencing other devices. And that's because these other devices won't transmit anything if another device is already sending something. So basically, if a continuous jammer is running and there's a proper Wi-Fi client, it's basically thinking, oh, this continuous jammer is running, let's wait with transmitting until it's finished. So that's why this attack is actually quite effective, because these devices are silenced and you don't really have to corrupt or mangle these other packets. So if we test this in practice, if we have a clear line of sight between the attacker and the victim, this specific device is effective up to 80 meters. And if we use a very cheap amplifier, we can even extend this to 120 meters. So I want to give a quick demo of this. Now, in principle, this is best done in the shielded room to avoid any interference. But something tells me it will work here as well, so we'll find out. But on a more serious note, I am only going to run it for a very short amount of time to prevent your connections from dropping or to cause any harmful interference. If it works, let's hope it works. Okay. Where is my mouse? So I now have two Wi-Fi devices. One of them will be used as the jammer, and the other one will be used to monitor the traffic that is going on. So let's first initialize these devices. And let's already start Wireshark on one of those devices. Something is wrong here. Yep. Will this work now? Yes. So we're currently monitoring the traffic in this room. This can be a little bit smaller. And we're now going to jam this traffic. So let's run our constant jammer on the other device. And normally all this traffic should now stop if it works correctly. And you can see there is no longer any traffic being sent. As I promised, I wouldn't run this too long, so I'm going to stop it now. So as you can see in Wireshark, if we go up here a little bit, we see here at around 30 seconds, our jammer injects the very first Wi-Fi packet. But after that, even though it's actually transmitting valid devices, we don't see any traffic at all. It's only once we stop this jammer that we again see Wi-Fi traffic occurring. So let's go back to the presentation. So the code of this constant jammer is not available publicly because it really disrupts any kind of network activity without usable countermeasures being public. So we didn't really want to give this to your script kiddies to really mess with your network, because that would be really quite annoying. But if you are a researcher and you want to use this to test something, you can contact us and we can give you the code. One interesting application is that this also works on a Raspberry Pi. So you can imagine just sticking your Wi-Fi dongle inside a Raspberry Pi, attach a battery pack, and you can simply drop this wherever you want. I don't recommend doing it, but in principle it's possible. So what are some practical implications of this? In other words, what are the type of devices we can jam? Well, one important remark is that we're not just limited to jamming Wi-Fi devices. Basically, we can jam anything in the 2.4 and 5 gigahertz band. So common protocols are, for example, Bluetooth and Zigbee. On what kind of devices use this? Well, we have the Internet of Things, we have home automation systems, we have sometimes even industrial control systems which use these frequency bands and we can jam them. Perhaps an example a bit more closer to home. These days you also have these fancy baby monitors which actually show a live video feed. And the frequency bands that are used by Wi-Fi are sometimes also used by these devices. And then a bit more serious again, there are also some security websites and I think also some alarm systems of cars, or at least the unlock key signal of your key fob, that I think some of those devices will also use the 2.4 or 5 gigahertz band. So in principle, we could jam these as well, even if they are using a different protocol than Wi-Fi. And no, it's not just wild speculations that attackers would use jammers. If we look in practice, we actually see that if there are cheap jammers possible, attackers and thieves might start using them. One example is KeyCar is a jammer for your unlock key for cars. There were actually a few thieves that were using a very cheap jammer imported from China, and they were jamming the unlock signal of your car. So basically, you're walking away from your car, you locked it, you think, all right, it's locked, but actually that signal was jammed, and they can now enter your car. An example related to this, certain cars actually have an anti-theft device, which is a GPS device which tracks the location and is able to inform the owner of the car where this car is currently located on the earth. Of course, for thieves, that's quite annoying. So what they used is they used a simple GPS jammer to basically disable this anti-theft GPS device. And even in a more crazier example, in my opinion, you had two guys that wanted to rob a store. The first thing they did is they cut the hardline phone cables. The second thing they did is they cut the actual alarm cables. And they even went beyond that. They even bought a high-power jammer to also jam the mobile phones. And all this just to ensure that whoever was inside the store was not able to contact the outside world. So just to show you, people do use these jammers if they are cheap enough and if they provide an advantage. So it's not just wild speculation. Okay, that covers the reactive jammer. We are now going to implement the selective jammer. And just as a reminder, what is a selective jammer? Well, a selective jammer is able to block specific packets. It won't just jam the complete channel, but only packets, for example, coming from a certain device or being sent to a certain device. And what are the steps we need to do in order to implement this using our devices? Well, the first thing we need to do is we need to detect a new incoming transmission, and then we need to decode the header of this packet. And once we have decided to jam this packet, we have to initialize our jammer. Basically, we have to stop receiving the current frame and put our antenna into transmit mode. And then we simply inject a dummy packet to jam the remaining content of this packet. So this selective jammer only jams the final bytes of a packet. However, because there is a CRC checksum calculated over this complete packet, the receiver will notice that, okay, the CRC is invalid, so I will drop the complete packet. So even though we're only jamming the last byte, the complete packet will be dropped by the receiver. So it turns out that point 2 or 3 are actually very easy to do using our devices. It's point 1, which is decoding the header of a packet while it is still in the air. That is very difficult to do using our cheap devices. But of course, I'm giving the talk here, so we managed to pull this off anyway. What's the important realization in order to accomplish this? Well, that's that our Wi-Fi dongle actually contains two chips, like I already mentioned before. We have our radio chip, which takes the incoming physical signal and decodes it to a Wi-Fi frame, and we have our second CPU. And what happens when we are receiving a frame is that this radio chip will simply use direct memory access to write the contents of the packet to the memory. And while this is happening, we can actually take full control over the internal CPU. So what can we do? Well, we simply monitor this memory until we notice that the Wi-Fi chip is writing these decoded bytes of the packet. So basically, we first put a dummy 0 value inside the memory. Once we notice that it is being changed, we know that a frame is in the process of being received. So with this clever little trick, we can actually detect when a frame is being received, and we can also decode parts of the frame simply by reading the memory. Okay, so I wanted to explain also a bit about how we actually do this in practice. So in practice, first we have to decode the packet, so we have a while loop to detect when this memory will change. So basically, we first avoid a timeout that we stuck in this loop infinitely. Then we check whether bytes are being written to the memory. And finally, well, not finally, once we know that a frame is being received, we can start decoding the header, but decoding is already done. We simply can read the memory, and we can, for example, check, is it a probe request or is it a beacon? And then we can also see, do we want to jam this frame or not? Basically, we compare the MAC address of the sender of this packet with the MAC address of the source that we want to attack. And if we indeed want to block this frame, we will stop receiving the current frame. Again, this is not that hard once you know what you have to do. To stop receiving the frame, you simply take this register and set the correct bit, and you basically stop receiving the frame. And finally, injecting the dummy packet, you basically write the address of the packet you want to inject to one of these registers, and then you set the correct bit in the TXE register, which stands for transmit enable, basically start sending the packet. And this is the code that we actually implemented in the firmware in order to pull this off. So we did a few experiments with this. We jammed beacons using several devices and over several positions. And the main question is, how reliable is it? And to answer that, we basically have to find out what is the first position of bytes that are mangled. And it turns out that for beacons sent at 1 megabit per second, our jammer is fast enough to already start corrupting bytes at position 52 inside these beacons. If we have beacons in the 5 gigahertz band, those are sent at a higher bit rate, and that also means that the position where we first start corrupting bytes is a bit later into the packet. To give an overview, we only start jamming the packet once we have decoded the header. So only after we have received 34 bytes do we really initialize the jammer. So in my opinion, this is actually quite fast, because normally a Wi-Fi transmission is of the order of, let's say, 200 to 500 microseconds, but within this time we can pull off this selective jamming. So to conclude this part, at least the theoretical discussion, making a selective jammer 100% reliable is really difficult. You're always going to miss some packets. Additionally, we can also only jam medium to large packet, because if your packet is too short, we simply don't have enough time to actually activate our jammer and decode the remaining content. And in my opinion, it's very surprising this is possible using a very cheap device, because you also have a very limited API to work with, but still we managed to pull it off. So to come back to this domino defense system, it is actually able to defend against this kind of attacks, but I don't know if I have the time to explain this in detail, so I'm going to skip this for now. And I'm going to immediately continue with the demo. So what I'm going to do is I have installed a router on a 5 gigahertz channel, which is relatively unused, and I will try to reactively jam the beacons of this device. So again, as a reminder, in principle, you should do this in a shielded room to avoid any interference. We're again going to do this for a short amount of time. And I hope this will work because this is, as you can imagine, a bit more difficult to pull off than the constant jammer. So I first have to going to use devices which work in the 5 gigahertz band. And I actually have these two devices. They are running the same firmware. They are just able to also operate in the 5 gigahertz band. I do have to configure this, so this might take a small minute. So as you can also see in my previous demo, we are actually running this inside a virtual machine. And that is the advantage of having these USB devices. You can simply download the virtual machine that we created and simply plug in your device and you can use them. There is no need to install custom drivers yourself and so on. It's basically plug and play once you have the firmware and the driver source code. Okay, let me close this. So the first thing that we're going to do is we're going to, again, configure these devices first so they are ready to transmit. So in this case, we're going to use a reactive jammer. Basically, a reactive jammer is exactly the same thing as a selective jammer. One device did not get detected by VMware, so let's just plug in the devices again. So we can see we have a virtual machine and both the Wi-Fi devices are now connected. So let's try this again. It seems to be working now. So now I have to again start. Why is this happening? This works as well. So let's start capturing on the first interface. And you can see there is some background traffic going on. I'm going to filter so we are only showing the access point that I put up myself, which has as name test network, and we're going to try to reactively jam that. For some reason this is always behaving weird during demos, I don't know why. Yeah, you will see it during the attack anyway. So, okay, we can now activate our reactive jammer and cross our fingers that it works. So we are going to use interface 3 and we're going to jam the test network. Of course, we need root to do this. And as you can see, there are no longer any beacons being transmitted, so our attack actually works. We are currently jamming these beacons. As you can see, they are not present at all in our Wireshark dump. And that is because currently Linux is actually dropping packets which have an invalid CRC. If we instruct Linux to also show packets which have a bad CRC, I'll have to write it from the top of my head. This is WLAN2 set. There we go. We now instructed Linux to only also display package which have an incorrect CRC. And you can see that, yes, these beacons are being transmitted. However, their checksum is wrong. So if you look at this inside Wireshark, we will see here somewhere, if I can open this. You will see here, the frame check sequence is indeed wrong, and this packet is not actually being received properly. So we can now stop our jammer. I'm simply going to unplug the devices. No, that's actually a bad idea. So let's stop the constant jammer. This can actually take a few seconds, but in this case it doesn't. Perfect. And now you can see that Wireshark no longer displays these frames in red. We stopped our reactive jammers and the beacons are now being received properly. So that covers the demo. So the code of this reactive jammer is available online. You can visit the following website, and it has a link to both a virtual machine which you can download, which has everything pre-installed, and there is also a link to the source code. There are a few fun things you can do with this, but I don't think I have the time to explain them because the demo took a bit longer than expected. But these slides will be online, so you can view these slides to get an idea of what you can really do with this. Basically, you can attack Wi-Fi geolocation by injecting your own SSIDs and by jamming nearby SSIDs. And what you can also do is, for example, try to jam rogue access points. And okay, so now we have a few minutes to explain how these low-layer attacks can actually influence attacks on high-level protocols. So basically the question is, what if we could use these devices to reliably manipulate encrypted traffic? Again, I want to stress that we first simply want to manipulate traffic, we're not yet going to decrypt it. Well, if we could do this, we could actually break WPA TKIP. Well, break is actually a big word. We could launch an attack against it. So what are we going to present now? Basically, we're going to present a channel-based man-in-the-middle attack, which will work against any encrypted network and allows us to reliably drop or manipulate frames. So let's start with basically a strawman approach. Let's say we want to man-in-the-middle the traffic between an access point and a client. We could simply clone this rogue access point on a different MAC address and then simply forward the traffic between those devices. And also the client we are spoofing will also have a different MAC address. However, that will fail because the handshake used by WPA and WPA2 actually verifies the MAC address, so this attack is detected. In other words, we have to use the same MAC address as the devices we are trying to man in the middle. So let's say that we use the same MAC address as these devices. Then we have a real annoying problem. All these devices are operating in the same channel, and basically the traffic won't go through us. They will simply directly communicate with each other. So that's also not possible. How do we solve this? Well, as the name implies, we're going to clone the rogue access point on a different channel. And that allows us to use the same MAC address as the original access point. However, because it's on a different channel, all the traffic that the client is transmitting will only be received by us, and we can forward this traffic over the different channel. And in this case, the handshake will succeed, and we can reliably intercept traffic. So we can use this to attack WPA TKIP. A quick introduction, what is this protocol? Basically, you previously had the old web protocol, which is horribly broken. Then a few standards came up, and one of those was TKIP, which was basically a protocol designed to run on this old web hardware, but still provide decent security. And finally, we have the secure AES version. And that means, well, I said that this is an intermediate protocol, so is this still being used? Why are you researching that? Because many people think that these two aren't really used anymore, and basically everyone uses this one. It turns out that's not the case. And why is that? Well, if you have a network, you can basically configure it to allow both TKIP and CCMP. This is the AES variant, so all devices can connect as well as new devices. This sounds very well, but this is only the case for unicast traffic. If you look at broadcast traffic, it has to be received by every device. This means it has to be TKIP, so even all devices can decode it. In other words, if your network supports both TKIP and the AES CCMP variant, TKIP will be used to encrypt broadcast traffic. And we did a quick experiment. We monitored Wi-Fi networks nearby, and we found that more than 2/3 of networks actually will use TKIP to encrypt their broadcast traffic, which is a very significant amount, so it's still widely used. So to give a very quick explanation of the attack, Basically, what TKIP does, it first calculates a message integrity check, it then uses RC4 to encrypt the packet. And by the way, don't use RC4. We have shown that is actually completely broken. Well, not completely, but you can decrypt cookies on stuff, so stop using it. The problem with this protocol is that if you manage to decrypt this packet, you can actually reveal a key. So if you manage to decrypt the packet, basically part of the security is lost. The designers realized this and they implemented a countermeasure which basically states that if there is a MIC failure, if this checksum is wrong, you should issue a warning. And what happens if there are 2 of these issues within a minute, the access point will stop all traffic as a countermeasure to try to slow down attacks. It's the access point that makes this decision, and in order for the access point to make this decision, it needs to know when the client encounters an error when decoding this MIC value, and this is done by the client sending a so-called MIC failure report. I'm not going into detail here. Basically, these MIC failure reports can be used to decrypt these packets, and if there are more than 2 MIC failures reported, all traffic is stopped for 1 minute. The problem is, if we apply this to broadcast traffic, let's say there are 6 devices connected. If we send one package which causes one of these MIC failures, we actually get 6 replies, and these countermeasures would immediately activate. So what we will do is we'll use this channel-based man-in-the-middle attack to capture these MIC failures reports. However, we will not forward them to the access point, so these countermeasures will not be triggered. And again, I'm not going into detail. You can also read about this attack on the paper, which I showed on the URL. It will also be visible at the end of the talk. Basically, using our channel-based man-in-the-middle attack, we can attack this TKIP encryption. So only use AES CCMP. So I think I'm almost out of time because the demos took a bit longer. So I'm going to want to have some room for questions, so I have to skip this. This is really the last part. Basically, this last part covered that the FCC recently proposed a rule to implement certain firmware security. However, you may have heard that there is a lot of controversy around that. And I'm writing a blog post essentially about it, which I will release in a few days. But unfortunately, I don't have the time to discuss it in detail. So to conclude the talk, if you want to run the reactive jammer yourself or want to have more information about these attacks, you can visit this website, you can ask me questions on Twitter, or you can ask your questions right now. Thank you for listening.
There's still time for 1 or 2 questions, so...
Hi, thanks for the talk. Nowadays, most of the APs that detect the channel they emit on automatically based on the, well, I guess the less crowded one. Mm-hmm. Can you use that to make all other APs but yours to think that this one is crowded, so you keep the channel for yourself in the neighborhood?
It depends. So the question, I think, was that some access points are first going to monitor the channel and see which channel is not in use, basically, and they will use that channel, right?
Exactly.
Yes. So I think if you're able to jam a channel when this decision is being made, you can influence that decision. For example, if you want to use channel 1, you can turn on your jammer on that channel, so all the access point will select a different channel, and afterwards you can use channel 1 just for yourself. I think the difficult part in that is knowing when that access point will make that decision when it is searching for the most optimal channel. So I think
detect at what time they're just jamming at this exact moment.
Yeah, the problem is trying to guess when the access point is monitoring the channels to see which one it best uses, because you can't keep jamming your own channel forever, because then it's unusable for yourself.
I was thinking about the selective jamming. Can you say, let's say, if that's the access point, any access point but mine are going to be selectively jammed, so they will just use another channel?
Maybe, I don't know.
Okay, we'll take this discussion offline then.
Okay.
Thank you.